Hey everybody, it's Ripley back again. Today I'm going to show you how to find the area between curves on a closed interval, because clearly it's got to be on a closed interval, right? You got to have some area that's bounded. So what we want to do is, let's say that these two curves intersect here at A, or they intersect here at B, and they intersect here at B, and I want to figure out what the area between them is. It's actually quite easy. It's almost boringly so. All right, if you recall, back when we found the area under a curve, like in this case f, right, all that we did is we took a big old rectangle like that at some x star sub I value, and we just added them up. We added up an infinite number of infinitely thin things from A to B. Well, we're going to do exactly the same thing in this, except what we're going to do is we are going to take a slice of action that looks like that. Ooh, there's slice of action. That's going to come up again and again over the course of the next few lessons. This slice of action is what I refer to as this little rectangle that's framed in by the two curves themselves. So if you recall, if I wanted the area under a curve, if I took the integral from A to B, from A to B of f of x dx, I knew that this was the limit as n went to infinity, the sum as I goes from 1 to n of f of x sub I delta x, right? And then all I did was add up. This said add up, bunch of rectangles. How many of them? An infinite number of them. Well, all we're going to add up now is these same things, only the difference this time is instead of just f of x sub I, what I'm going to have is, if you notice, this distance is f of x sub I minus g of x sub I. So if I want, minus, there should be my minus right there, minus g of x sub I. That's all it is. It still has a thickness of delta x. So if I want the area between the curves, this would just be the limit as n goes to infinity of the sum as I goes from 1 to n of f of x sub I minus g of x sub I, the whole thing, times delta x, where of course delta x equals b minus a over n. Or this is equal to the integral from a to b of f of x minus g of x dx. And we're done. That's it. Now the most important thing is that you acknowledge this piece of action, because this is going to be important when we get into things like volumes, which is down the road. The other thing that we got to make sure that we understand is that this is f of x minus g of x because f of x is on top. F of x is farther away from the x-axis, which means this height is supposed to be a height, right? Because it's supposed to be an area. This height is definitely going to be positive. So in this case right here, if I want this to represent the area, I got to make sure that f of x is greater than g of x, true? So let's say that I had a function, let's go back here, build myself a function, that instead looks something like this. Whoop. This is going to be f of x, and then whoop, and this guy's going to be g of x. And then I'm going to call this a, I'm going to call this b, and way out here, I'm going to call this C. Now what would I do? Well, again, I've got a slice of action here, and the slice of action, let's see, I got to figure this out. The top curve is F, so this is going to be for some x sub I. This is going to be f of x sub I minus g of x sub I. That's going to be that height. And then over yonder, I'm going to have this guy, if you notice, on top, this is going to be, I don't like the what. I'm going to cheat a little bit and call this, well, let's call this x sub j. Who cares, right? That changes because now g is on top. G is farther away from the x-axis than f is. So this would be g of x sub I minus f of x sub I. So when we're integrating by hand, if I want the total area bounded between the two curves, I would have to write it as two integrals. The integral from a to b of f minus g dx plus, because areas are additive, right, if I want to get them, the integral from b to c of g of x minus f of x dx. Now, a fancy way to do this, especially if you're using a computer algebra system or your calculator, is to write the integral from a to b of the absolute value of f of x minus g of x dx. That works as well. You could actually do that with the area between one curve and the x-axis, right? If I wanted to figure out, let's say, this is this right here, this is f of x, and I wanted to figure out the area from A to B, but I've got all this negative. If you think about it, I could easily take the area and simply integrate from A to B. Instead of just f of x, I could write the absolute value of f of x dx, because then what that would do is it would flip this negative part across. But that's really hard to do analytically, right? Algebraically, by hand. If I've got a computer algebra system doing it for me, or if I'm using my TI-84, which you should all do a little bit of research and make sure that if you've not already been taught by your instructors, you should do some research into how to take a definite integral by hand. All right? Okay, let's see. So I think that about sums it up. I want to do one little example for you guys just because they're fun to do. And let me, I'm sorry, you guys, I'm looking at my notes to make sure that I covered everything that I want to cover. And it appears that I sort of did. Let me just do one example with you. And then there's one other thing I want to talk about, which doesn't take very long. Let's do find area between y equals 2x and y equals root x. And we know it looks like this. And I know y equals root x looks like this. And I know that y equals 2x badly drawn, really badly drawn, looks like that. Ugh, yeah, this is one thing that I will tell you is, let's see, this is going to be y equals 2x, is try to make your slices of action, your area where your action is taking place, as exaggerated and thick as you possibly can. Because then it's easier to see what's going on. Like, I probably should have drawn that, just super exaggerated like that, because then you've got this little slice of action right here. Now, you're probably noticing, let me go back to black, you're probably noticing that it's really important if I'm going to find out the area between those curves. Another way you may see this written is bounded. It's bounded by. That means it's basically hemmed in. You could draw a circle around it, right? These two curves is to figure out where they intersect. Now, I know you realize that they intersect at 0, 0, and at 2, 4. Or, wait, did I screw that up? 4, well, 2, yeah, no, wait, it's not as intuitive as I meant to do it. Let's check it out. The way in which you solve this is you set 2x equal to root x, right? Wait, it is 4, isn't it? Oh, yeah. Don't listen to me. I'm losing my mind. So this becomes 4x squared equals x. I factor it over. I get, I'm going to factor out a, I'm going to factor out, I'm going to get 4x squared minus x equals 0. Factor out an x, and I get 4x minus 1 is equal to 0. So I get x equals 0 and x equals 1/4. Good Lord, what a mess that was. This is typically what I do, you guys, is I put an x squared here. So when I do x squared, then it's at 0 and 2. So I know this point of intersection is going to be 1/4, 1/2, right? So the only reason I did that is to figure out what my bounds are. I think it's sometimes good to see, good for you guys to see an instructor screw up on this stuff, talk themselves down a rabbit hole. It shows A, that we're human, and B, that you guys shouldn't feel too terribly when you make silly mistakes, because we do it, we all do it. Okay, anyway, I want to find the area, and the area is going to equal the integral from 0 to 1/4, right? That's the value of x. Those are the limits. Again, if you're like, whoa, what are my limits? What's going on? Should I use 1/2 or 1/4? Well, remember, this is delta x, which tells me everything should be in terms of x, from limits to functions to the dx at the end. So this is going to be 1/4. I need to take the bigger function, which is root x, and I need to subtract the littler function, which is, 2x. And then I slap a dx on there, and then I just follow the end of my nose, and I get 2/3 x to the 3/2 minus x squared from 0 to 1/4. And this is going to equal, let's see, 2/3 times, I'm going to put this in as 1/4 to the 3/2 minus 1/4 squared minus, and then here it's relatively easy to see that this thing turns into 0 minus 0, right? So let's do this guy together really quickly. This is going to be 2/3. Now, how do I do 1/4 to the 3/2? Students so often freak out about this, but you got to remember that x to the a over b is equal to the bth root of x to the a, or the bth root of x, the whole thing to the a. So I'm going to use this guy because I can take the square root of 1/4, which is 1/2, and then cube it, right? So 1/2, this is going to turn into 2/3 times 1/2 cubed minus 1/16. And this is equal to, well, one of these 1/2s cancels with that 2, and that's going to turn that into, so 1/4, this is 1/12 minus 1/16. So this is 4/48 minus 3/48, so this turns into 1/48. I'm done. You know what? I got time. I might as well do it. I'm going to show you how to do this on the TI just to see if we get the same answer. So we'll wait this thing. And for those of you that may not yet know how to do it, let's clear that off. Remember when we did that with derivatives. So all I do is I go to math, and then I'm going to go up because it's easier than going down. I'm going to do FNINT, so I hit 9, and look at that. Isn't that pretty? So I'm going to go from 0 up. All I do is fill in the blanks. I'm going to go from 0 up to 0.25, and then I cruise over, and this is going to be the second square root of x. Got to get outside the square root or I'll screw that up. Minus 2x, and then it's going to be dx. Put the x in there. I hit enter. I'm going to get a decimal, but you guys all know hopefully how to get from a fraction. Let's see, I want to get to a fraction. Hit enter, and I hit enter. Whoops, I need to go the other way, don't I? So let's go to a fraction. Wait, to a decimal. Is that right? Let's try that. 2, enter. Enter. Wait, what did I do? Let's just go 1/48 and see if it gives me the same value. Boom, yeah, it does. So this is different because it's done numerically in our calculator, and that's why the calculator couldn't come up with this value, but you should be able to see that this is an approximation. All right, so that's kind of cool because you got to see how to take a definite interval using your calculator. You know how to check your work, so you should be good. All right, one last thing, and then we are done. What if I don't have functions of x, but I have functions of y? So let's say that I have some function here, and let's change my colors, make it interesting. Now I've got, here we go, I've got, this is going to be f of y, and then we'll change the colors, oops, and this is going to be g of y. All right, you got to be a little bit careful, and you may have to turn your head. Well, there's no way that I can describe these as functions of x because they don't pass the vertical line test, right? So what I do is I draw a slice of action, but the slice of action can't be vertical because I cannot describe them as functions of x. So I draw a horizontal slice of action. And instead of calling this some value of x down here, this is going to be some y sub I, isn't it? True? The thing that is most important is that this is not delta x anymore. It's delta y. It's change in y because that tells me everything. So when I find the area in between, when I find this area in between, I'm doing everything as with y. So my limits are going to be on y. So let's say that this guy down here is going to be a, this guy up here is going to be b. It's going to be the integral from a to b of what? Now, which one's bigger? Because you're like, wait, you're used to looking farther up. Well, when we have functions of y, it's not farther up that wins, it's farther right that wins. So in this case, clearly, f of y is greater than g of y on the interval from a to b, right? Because it's the blue guy, it's farther right, minus g of y dy. All right? It's funny, I've been teaching for 21 years now, and when I teach this to students and I give them functions of y instead of functions of x, invariably every kid sort of twists his head, leans his head over, and makes me laugh every time. All right, thank you for your time and attention. I hope that was helpful, and I hope to see you in the next lesson. Have a great day.